So now let's talk about charging a capacitor. So let's say that we have a power supply right here, and we have a capacitor, and we have a resistor. There's always some resistance. The power supply has an EMF of E, capacitance C, resistance R. We close the switch, now current starts flowing. Okay, so minus plus, okay, so that means we're getting positive charge on this side, negative charge on that side, current's flowing this way, okay, and so if I do a Kirchhoff loop, start here and go around, we got the EMF, we got minus the voltage on the capacitor, minus the voltage on the resistor equals 0. Okay, so that's going to be the EMF minus the Q over C, the charge that's on the capacitor at a particular moment in time, minus IR. Okay, now I is the rate of change of the charge. The charge is increasing, so the dq dt is positive, so we can just go ahead and say that this is now minus Q over C minus dq dt, R equals 0. Okay, so what we want to do is do a little bit of algebra here. So let's isolate this dq dt. Let's isolate the dq dt to one side of the equation. So dq dt, okay, is going to be equal to 1 over RC times C times the EMF minus Q. Okay. All right. Now, at that point, we have to look at this and say, well, let's do a little more algebra here. Let's say that dq over C EMF minus Q equals 1 over RC dq. Oh, sorry, dt. So now we do an integral. We can do an integral from 0 up to the final charge, whatever that's going to be here, okay? And so we can call that like Qm for the maximum charge, and that's going to be at some time t. Okay, so the integral dt is just real easy. From 0 to t, that's just t. The problem is the other integral. So we look at it, and we look in the back of the book at an integral table, integration by integral table. Okay. Integral dx over a plus bx, according to the back of the book, is 1 over b times the natural log of a plus bx. Okay, so our integral here, integral of dq over c times EMF minus Q. Okay, so that means the A is going to be C times EMF. The B is going to be minus 1. So that's going to be minus natural log of C times EMF minus Q. And we evaluate that at 0 and Q max. Okay. So that's going to be natural log of C times EMF minus the natural log of C times EMF minus Q, and that's going to equal T over RC. Okay, so this is the natural log of C times EMF over C times EMF minus Q, evaluated here. Okay, so that's T over RC. Okay, and so now you look at this and say, what is C times EMF? Well, we got a capacitor here, and we're charging the capacitor here. The ultimate biggest charge that can be on the capacitor is going to be, some Q max, and that's going to occur when this voltage is equal to the EMF. We know that Q equals C times V. Okay, so C times EMF is going to be the maximum charge. And so we have the natural log of the maximum charge over the maximum charge minus the charge at some moment in time is going to be equal to T over RC. Okay, so we get rid of the natural log, so that's Qm over Qm minus Q, and that's equal E to the T over RC. Okay, now I want to solve for Q, so what I'm doing is I want to get Q all by itself here, so I'm going to take the reciprocal of both sides, so this is Qm minus Q over Qm, and that's going to be E to the minus T over RC. Cross multiply, Qm minus Q equals Qm E to the minus T over RC, or Q, solving for Q, that's going to be Qm times 1 minus E to the minus T over RC. Okay, so that gives us the charge on the capacitor at some moment in time. Notice the RC. That's going to be the same tau that we had before. So Q is going to be Q max, okay, times 1 minus E to the minus T over tau. Tau is still our time constant. Equal to RC. Okay, so this is the charging on that capacitor. So the charge that's on the capacitor, and again, we can just multiply here by the voltage, or rather by the capacitance here, or rather divide by the capacitance here to get the voltage. And so anyway, so it's pretty straightforward here how you find, as you're charging the capacitor. So this is analogous to the discharging that we had before in the previous example. And notice if you graph that, okay, what's the charge on the capacitor? And that's related to the voltage on the capacitor. Okay, it turns out to be asymptotically approaching that Q max right there. And so as you go successively in time, you get closer and closer to the Q max. It means you never really, because asymptotic approaches it means you never really fully charge the capacitor. You're getting it more and more charged as time passes, but you never actually fully charge it. There's always room in there for one more electron. No matter how many electrons you put in there, you can always squeeze one more in. And so it just gets very slow charging at that point, because obviously if you take the derivative of this curve when it's way over here, the derivative is very, very small, and so the current is very, very small. When you first close the switch, the current is going to be very high. So look at this. Okay, so we got the capacitor in here. We got the resistor. When you first close the switch, the voltage on the capacitor is 0, so there's no charge, and so that means all the voltage is across here. So that means the current is going to be equal to V over R at first, but the current is going to be dropping rapidly. It's going to be dropping rapidly close to 0 here. Because we said that the Q here, that's the charge that's on the capacitor, is Q max 1 minus E to the minus T over tau, okay? And so you take a derivative of that, dq dt, okay? And that's going to be equal to, what is that? That's going to be Qm over tau, E to the minus T over tau. Okay, so that means that it's dropping exponentially. Units would be amps, because this would be coulombs and that'd be seconds. So coulombs per second would be units of amps.